Good morning, children. In the previous lecture, we were discussing about relative density, but due to some technical reasons, the discussion was not completed. So let's start the discussion about relative density once again. Now, when we talk about relative density, earlier we discussed about density in the previous lecture. Now, how relative density is different from the physical quantity or from the term density. Now, if you look at this term, relative density, the term itself is self explanatory. Relative density means it is actually the ratio of the density of a substance to the density of pure water. Now, pure water and at 4 degrees Celsius. The definition is the relative density of a substance is defined as the ratio of the density of the substance to the density of pure water at 4 degrees Celsius. And relative density is also known as specific gravity of the substance. So what my point is, relative density, the term itself is self-explanatory, means it is a density in relation to a particular substance, in comparison to a particular substance. But that, what is that particular substance? That particular substance is pure water, and that too at a particular temperature, and that is 4 degrees Celsius. So these two things you need to remember. First, it is the density of a substance in comparison, relative. The term relative is attached over there as a prefix. Relative to pure water at 4 degrees Celsius, relative to the density of pure water at 4 degrees Celsius. And it is also known by one more name, and that is specific gravity of that particular substance. So, going by the definition, relative density is the density of a substance upon density of pure water at 4 degrees Celsius. Now, as you can look into this relation, it is a ratio of two similar physical quantities: density of substance, density of pure water. Density in the numerator, density in the denominator. As a result, what happens? The units will be cancelled out, and this is the reason why relative density has no unit. Relative density is only a number. It never has any unit. But then another question, what is the importance of relative density? Though it is only a number, it gives you a clear idea that how many times a substance is denser, or rather heavier, than pure water at 4 degrees Celsius. This is one of the very important practical applications of relative density. Now, determining the relative density of a liquid. How we find out the relative density of an unknown liquid? The relative density of a liquid is determined using a very special bottle, which is called a specific gravity bottle, or RD bottle. Now, how we find out the relative density? By using a relative density bottle or a specific gravity bottle. Let's take an example. Suppose we take a empty and dry relative density bottle. We weigh it accurately. And how can we weigh it accurately? By using a instrument which is used to measure the mass. And what is that instrument? We have already discussed physical balance. Okay, so we take an empty dry relative density bottle, we weigh it accurately along with the stopper on a physical balance. Suppose the mass of that empty density bottle is m1. Now the next step, what we do, we fill up that empty density bottle with water, pure water, and now we insert the stopper. The moment we are going to insert the stopper, there will be some extra water that overflows and through the hole in that stopper. So what we do, we dry out the surface and then measure the mass of relative density bottle again on the physical balance. But what is the difference between measuring the mass of the relative density this time and in the previous case? The difference is over here, this M1 was the mass of the empty relative density bottle, and over here this mass M2. Now when we are going to weigh the mass again with the help of physical balance, this mass M2 includes the mass of pure water as well, because over here the density bottle, relative density bottle, is completely filled with pure water. So this mass M2 is the combined mass of pure water as well as the density bottle, and this M1 is the mass of only dry empty relative density bottle along with the stopper. Is it clear? This M2 includes the mass of empty density bottle as well as water. Over here M1 is the mass of only the empty dry density bottle. Then what we do, the next step will be, again we empty the bottle and now we dry it with hot air. Now we fill this empty relative density bottle with the unknown liquid which has been given to us, whose relative density we have to find. Suppose, say it is kerosene oil has been given to us and we are asked to find the relative density of this kerosene oil. We are not told the relative density, we have to find the relative density of this kerosene oil. So now what we do, we fill this empty dry density bottle with kerosene oil. Again we insert the stopper, again there will be some extra oil which would be overflowing, and again we dry it once more and weigh the bottle again. Now suppose the mass recorded this time is M3. Okay, then what is the difference between this mass M3, this mass M2 and this mass M1? What is the difference? The difference is, over here mass M1, this M1 was the mass, or rather is the mass of empty dry density bottle, RD bottle. This M2 is the mass of combined mass of empty density bottle plus the water that is filled inside it, while this M3 is the mass of density bottle as well as the mass of the unknown liquid, which in this case is kerosene oil. We have taken the example of kerosene oil, we can take any other example also, no problem. Is it clear? So this is M1, M2 and M3. Okay, now the observations. As I said, we can write the observations as follows. Mass of empty relative density bottle was M1. Mass of relative density when it was filled completely with pure water, so it was M2. So this M2 is mass of relative density bottle plus water. Again I repeat, mass of empty density bottle was M1. M2 is the mass of bottle plus water. Clear? And then when the empty density bottle was completely dried and then again it was filled completely with the unknown liquid, which in this case, which in our experiment we have taken kerosene oil, and then it was weighed again on a physical balance, the new mass recorded was M3. So this M3 is the combined mass of relative density bottle plus the unknown liquid, which in this case is the oil. Is it clear? So now what will be the mass of only water? Now this M2 is the combined mass of bottle plus water. If from this mass M2 we subtract the value of mass of RD bottle, we will definitely get the mass of water that is filled inside. So that is what we have done over here. Mass of water will be equal to the combined mass of water and the density bottle minus, means we will subtract the mass of only bottle from here. So M2 minus M1. Similarly, mass of kerosene oil will be combined mass M3, combined mass of unknown liquid, that is kerosene oil, plus density bottle minus mass of only bottle. Clear? Now, why we are doing this? Because we have to calculate, our objective is to calculate the relative density of that particular unknown liquid, which in this case we have taken as kerosene oil. Now, relative density is equal to, we know, density of substance upon density of pure water. This we have already discussed many times. But we know one more thing. We started, now just try to recollect what we have discussed in the previous lecture. Density itself is a ratio of mass upon volume. So density of substance will be mass of substance upon divided by volume. Again, density of pure water will be mass of water divided by volume. But why we are keeping this volume to be constant? Very simple. The reason is the bottle, the density bottle which we have taken, this relates to the volume of the density bottle which we have taken in our experiment. This volume will be equal to the capacity of the density bottle, because the bottle was completely filled with the water as well as the unknown liquid, that is the kerosene oil, and this volume will also be numerically, it will be equal. So we can cancel out this term volume from the numerator as well as from the denominator. So what will be left behind? Mass of substance, mass of same volume of water. So this is another formula for calculating the relative density of a particular substance. So relative density of the kerosene oil, that is the unknown liquid which we have been given in order to calculate the relative density through this experiment. Relative density of kerosene oil will be mass of kerosene oil upon mass of equal volume of water, that is M3 minus M2, which we calculated from here, and M2 minus M1, which we calculated from here. And this in turn can be equal to, simply it can be related to the basic formula, density of kerosene oil upon density of pure water. So this is how we calculate the relative density of a unknown liquid. Unknown liquid could be any particular substance in liquid form, like kerosene oil or any other liquid can be given to us, and with the help of this simple calculation we can easily calculate the relative density of that particular substance. Now, moving on to the next concept, or rather you can say application, that why we have discussed the concepts of density, relative density. So what are its application? The density and relative density, they find application in the concept of sinking and flotation. Always remember that a solid body will float on a liquid if its density is less than the density of the liquid, while it will sink in a liquid if its density is more than the density of the liquid. This is a very, very important application. This is an important application. Like, it is always observed that it is easier to swim in seawater than in fresh water, because the density of seawater is greater than that of fresh water. And why it is so? Because we know that in seawater there are large amount of dissolved salts which are present, and this is the reason why, because of those dissolved salts, the density of seawater is always higher, is always more as compared to fresh water. So the higher will be the density, more will be the upthrust on the body, and therefore easier it will be for a person to swim. Another application, we observe that a very small iron needle, it sinks in water, but massive iron ships like the super tankers which carry oil from you can say, oil rich nations to those to developing countries, those super tankers are very, very large in size. They such a massive iron ship which is made up of iron, they can easily float. What is the reason? What could be the reason? At the same time, the small iron needle is sinking inside. It can sink inside. If it's kept on the surface of water, it will sink. The reason is the iron needle is compact and its density is much higher than the density of water. While ships, no matter they are very massive, very large in size, but they are constructed in such a way that they have large air spaces inside. They are mostly hollow from inside. So as a result, sufficient amount of air is trapped inside the ship, which makes their average density very low, or you can say rather lesser than the water in which or on over the surface of which they are floating. This is the reason why the ships are able to float, while at the same time iron needles, they easily sink. Now, the density of a particular state of matter also gets affected by temperature. Now, if we look again at the basic formula, we know density is a ratio. Density of a substance is a ratio of its mass per unit volume. Now from here we can find, suppose if we keep the mass as constant, we can find an inverse relation. Density is inversely proportional to volume, and we know if we are going to increase the temperature, what will happen? The kinetic energy of the molecules will be increased, the intermolecular spaces will be increased, and generally the substances expand on heating and contract on cooling, but their mass remains unchanged. So this variation of temperature can lead to variation of density, and as a result it gives rise to certain convectional currents. Convectional currents in what? Especially in liquids and in gases. Now, what happens due to convectional currents? See, when a fluid, like whether it is a liquid, whether it is a gas, when I'm saying fluid, it includes both liquids and gases both. When a fluid is heated, it expands and it becomes lighter. That is, density decreases due to thermal expansion. Now you can see the relation why it is happening, because see, when you are going to heat a particular substance, its volume is going to increase. Now when you are going to increase the volume, density is inversely related to the volume. If this is going to increase, density will be decreased, and if the volume is going to decrease, density will increase. So I'm saying, suppose when a fluid is heated, it will expand, means volume will increase, and due to increase in volume, the density is going to decrease. Now when the density is going to decrease, the fluid becomes lighter and it rises upward. The cold fluid, being heavier, moves downwards to take the place vacated by the hot fluid, and the cold fluid then gets heated and again moves upward. This creates a cycle. This creates a cycle of downward movement of the hot and cold fluid form currents in the medium known as convection currents. Is it clear? This is how the convection currents are formed. Now, what are the application of convection currents? We find that air conditioners are always installed in a room at some height. Why it is done so? The reason is because the cold air coming out of the air conditioner being heavier, it will definitely move downwards, and the hot air in the room, because it will be lighter as compared to that cold air, it will move upwards. So this circulation in the upward and the downward direction, definitely it will help in a better and a faster cooling of the airspace inside that particular room. So this is the reason why air conditioners are should be rather installed at a particular height inside a room, so that convection currents can help in a better and a faster cooling of that particular space. Then second one, ventilators are always fixed near the ceilings. Again, an application of convection currents. Why the ventilators are always fixed mostly near the ceilings? It is done so that the basic reason is that when we breathe out in a room, the surrounding air becomes warm and impure. Now, the warm air is always lighter, it will definitely rise and moves out through the ventilators. And so, cold air will enter through from in the inside the room through the windows and doors to take its place. Thus, a convection current will be formed, and there will be very good amount of ventilation inside that room. Then, next one, a refrigerator has a cooling chest near its top. Again, the reason is same, to assist the formation of convection current, because the air near the top in contact with the freezing chest, it gets cooled down. So the cold air being heavier, it comes down, and the hot air being lighter, it will definitely rise from the lower part to take the place of that colder air. Thus, convection current is set up, and the cold air from the cooling chest, which is coming down, cools the entire region of the refrigerator below the chest. Because the faster the convection currents will be formed, the faster and the better cooling will be there. So this is a brief discussion of the entire chapter. Now, definitely try to revise the concepts again and again, and then we will discuss with the exercises also. Thank you.